Hi, everybody. So, just a minute ago, we talked about atoms, all right, and the atomic numbers. The atomic number is the number of protons. You cannot change the number of protons for an element without changing the element, all right? So, for example, if you have six protons, you are carbon, but if you remove one, you turn into boron, right? Five protons. You can, however, change the number of neutrons and or change the number of electrons on an element. Sure. Let's talk about neutrons. Isotopes. That's the fun word, all right? Isotopes is the fun way of saying we have an element and we are going to add or remove neutrons from the element. All right? So, an isotope is an atom that has the same atomic number, right? Same number of protons, but different number of neutrons. Okay? So, with that said, is that natural? Yeah, that's normal. All right. So in the real world, if you look at the periodic table, for example, you will see that the atomic mass of these elements are like decimals, right? So you're going to see numbers that are like, like for example, like 25.21. Like what? Where's the 0.21 come in? How do you have a fraction of a neutron? You can't do that. The reason why is because the atomic weight or the atomic mass of an element is actually um, it is the weighted average of the different isotopes that are out there. So, for example, with carbon 14, that could be a thing, right? Carbon 12 is another type of carbon. Carbon 13 is another type of carbon, right? So it's still carbon, it's just may have a few more or a few less neutrons, right? Some isotopes are radioactive, meaning that there may be too many neutrons in it. So, with that said, it's likely to react. It's going to start to throw those neutrons off of it and become radioactive. Sorry, my dog just walked in. So that's the idea with neutrons and isotopes. Radioactive isotopes. What that means is you have an isotope, right, an element with a different number of neutrons, typically more, right, and that nucleus is spontaneously decaying. Meaning, let's say I have carbon. Carbon naturally has about 12 neutrons. But what if I have carbon 14? Some of you have heard of that before. What that means is it has extra neutrons, two extra in this case. So instead of 12, it has 14 neutrons. If it's more radioactive, what's going to happen is those extra neutrons are going to fly off of the atom, meaning that that's what makes it radioactive. Radioactive means that it's basically throwing different subatomic particles off it, whether they're electrons or neutrons. And we actually use some of these in the real world. We use these in medicine to help tag different things in the body, which I'll show you in a second. Um, my dog wanted to have a view here. So with that said, half life. All right, a half life is the time it takes for 50% of the atom to decay. Right. So if I have, let's say, 100 grams of uranium, how long is that going to take to go away? Well, we measure that in half life. So how long does it take for 50% of that uranium to decay? So in this case, if I had 100 grams of uranium, how long does it take so that there's only 50 grams left? How many minutes, days, hours, years, decades is it going to take? Sorry. With that said, here's what it looks like. Here's what that looks like. All right, ionizing radiation is when something is getting thrown off. In this case, you can see an electron being thrown off. In biology, there are different applications for isotopes. All right, you can have dating, right? So geological layers of the Earth, fossils typically use carbon for that one, so you can use that to figure out how old something is. But in the body, we can use radioactive tracers or biomarkers is another word we can for it. These chemicals are labeled with a radioactive isotope. So basically, you take a chemical and you toss a couple of these radioactive isotopes in. Think of it like a Lego block. Remember before we talked about elements being Legos? Think of it like a Lego block, except a little extra. Maybe I painted it with glow in the dark or a highlighter, right? So instead of having a yellow Lego block, I toss some highlighter on that and make it nice and bright yellow. I highlight it, right? What that does is it goes and still binds and creates different chemicals, right? And we can find that in the body. So if I were to use something like this in the body, I can actually find that specific molecule somewhere else, right? Because that one element is highlighted, right? It's a tracer molecule. Here we go, biomarkers, and these could be used for various things, such as diagnosing different diseases. All right, we can see these inside of a PET scanner. Um, the, because radioactivity can damage molecules, these isotopes can also be hazardous. This is not something that is always going to be used, right? But sometimes it is the only thing we can use. In some cases, such as cancer treatments, radioactive cobalt could be used. So instead of as a tag, it could be used to actually destroy cells, right? Intentionally try to kill off cancerous cells before they go too far. All right. So that's an idea right there with isotopes and how they're used in the body. Bottom line, isotopes is an element with more or less neutrons than normal, right? And they have different reactions that can occur.